Modern vehicles are no longer simple mechanical systems. They have evolved into software-defined platforms. Inside today's vehicle, multiple high-performance applications run together on shared hardware. For example, an IVI system handles media and navigation. An ADAS, Advanced Driver Assistance Systems, processes camera and radar data. And a gateway ECU, Electronic Control Unit, manages communication across networks. All of these can run on the same Linux-based system. Now this creates a critical challenge. Not every application can be trusted equally. A media app should never interfere with braking logic. A third-party app should never access vehicle communication buses. So the core question becomes, how do we strictly control what each software component is allowed to do? This is where access control models become fundamental. In this lecture, we will clearly understand DAC and MAC and why automotive systems cannot rely on DAC alone. DAC, or Discretionary Access Control, is the default security model used in Linux systems. In this model, the control of access is given to the owner of a file or process. This means, if a process creates a file, it decides who can read, write, or execute it. This is implemented using tools like chmod, which changes permissions, chown, which changes ownership, and umask, which defines default permissions. Now this model works well in traditional systems. But the problem begins when multiple applications share the same environment. Let us take a real automotive example. An IVI system writes logs into a file like /var/log/ev/media.log. Now imagine another application running with similar privileges. Because DFIC is based on user identity, that application can also modify the same log file. It can inject false data, corrupt system logs, or hide critical failures. This is extremely dangerous, because logs in automotive systems are often used for diagnostics, debugging, and even safety validation. So the core weakness of DAC is, it assumes that the owner will enforce correct access. But in a mixed trust environment, that assumption breaks completely. MAC, or Mandatory Access Control, solves this exact problem. Instead of allowing users to decide access, MAC introduces a system-level policy. This policy defines what actions are allowed and what are strictly forbidden. And the most important point is, these rules are enforced by the kernel itself, which means they cannot be overridden by any user, not even by root. This is a major shift in security design, because now access control is no longer optional, it is mandatory. In Linux, MAC is implemented using frameworks like SELinux, meaning Security Enhanced Linux, and AppArmor. These systems work by assigning labels to processes and resources, and then defining rules on how these labels can interact. For example, a process running in one domain may be allowed to read a file, but not execute it, not modify it, and not access network interfaces. In automotive systems, this becomes extremely powerful. Even if a tool has full file permissions, MAC can still block its behavior. For example, a diagnostic application may have access to a binary, but MAC can prevent it from executing that binary. This ensures strict isolation between components and prevents lateral movement across the system. Now let us clearly compare DAC and MAC. In DAC, access is controlled by the file owner. In MAC, access is controlled by system policy. In DAC, root user can bypass restrictions. In MAC, even root must follow policy. DAC is flexible, but weak. MAC is strict, but secure. From an automotive perspective, DAC provides a basic level of access control, but MAC provides enforcement guarantees. And in safety-critical systems, enforcement is far more important than flexibility. Let us now understand a real-world problem. In Linux systems, firewall rules are controlled using iptables. And by default, any privileged user, especially root, can execute iptables commands directly. Now think about this. In a vehicle, if any process can modify firewall rules, it can open or close communication channels. It can block critical services, or allow unauthorized traffic. And the worst part is, there is no strict audit or control. Changes can happen silently. This creates a serious security risk, especially in connected vehicles, where network behavior directly impacts safety and functionality. To solve this problem, we introduce MAC-based control using SELinux. The idea is to remove direct access completely. No process, not even root, should execute iptables directly. Instead, we introduce a trusted wrapper application called abs_iptable. Now, all firewall operations must go through this wrapper. This wrapper acts as a gatekeeper. It validates requests, executes commands in a controlled manner, and logs every action. This transforms an open system into a controlled pipeline, where execution is not just allowed, it is governed, monitored, and enforced. Now let us understand how this control is implemented. In SELinux, everything revolves around labels and domains. First, the wrapper binary is labeled as abs_iptable_exec_t. Then, it runs inside a domain called abs_iptable_t. And finally, the actual iptables binary is labeled as iptables_blocked_t. Now comes the key rule. Only the abs_iptable_t domain is allowed to execute iptables. No other domain can do it, even if permissions exist. This ensures that all execution is forced through a single controlled path. Let us see how this behaves at runtime. If a user tries to execute iptables directly, the system checks the policy and immediately denies the request, even if the user is root, because the policy says this action is not allowed. Now, if the same command is executed through the wrapper, SELinux performs a domain transition from an unconfined domain to abs_iptable_t. Inside this domain, execution is permitted, so the command succeeds. This clearly shows that execution is not based on permissions, it is based on policy. To make this even stronger, SELinux uses never allow rules. These rules define what must never happen in the system. For example, no domain, except the trusted one, can execute iptables. These rules are checked during policy compilation, which means they are enforced before the system even runs, and cannot be bypassed, not by privilege escalation, not by runtime manipulation. This provides a very strong security guarantee, which is essential for automotive systems. Another critical benefit is logging. Every time the wrapper executes a command, it records what was executed, who triggered it, and when it happened. This creates a full audit trail. In automotive systems, this is extremely important, because when something goes wrong, engineers must trace back the exact sequence of events. Without logging, security becomes invisible. With MAC, security becomes observable. Finally, we verify that everything works correctly. SELinux provides audit logs called AVC logs. These logs show when access is denied. At the kernel level, from the implementation, we observe direct execution of iptables is blocked. Execution through the wrapper is allowed. This confirms that the policy is active, and the system is behaving exactly as designed. Modern vehicles operate in a highly complex environment. They run third-party apps, handle OTA updates, process safety-critical data, all on the same platform. In such a system, DAC alone is not enough, because it relies on trust, and trust can be broken. MAC, on the other hand, enforces least privilege, prevents misuse, and ensures isolation. It is also essential for meeting industry standards, such as UNECE WP.29 and ISO SAE 21434, which define cybersecurity requirements for modern vehicles. So the conclusion is simple. MAC is not optional. It is a foundational requirement. DAC gives flexibility. MAC gives control. In automotive systems, control is critical, because safety depends on predictability, and predictability comes from enforced behavior, not from assumed trust.